Hello. Today we're going to talk about Green's theorem. So last time we went over the fundamental theorem of line integrals where we were told that we got independence of path. And that was only true for the situation where we have a conservative vector field. Okay, so that was the one biggie takeaway that we had, and we summarized it at the very end, where if we know that our vector function is conservative, then that's the first one that was on our list. Then our line integral will be independent of path, and that will also mean that we're dealing with a gradient vector function, and so we can use our fundamental theorem of line integrals. This time we're learning a theorem called Green's theorem. And Green's theorem relates a line integral around a curve to a double integral over a region. And so a little bit of terminology needs to come out. So notice this little green blob, and inside it's called D. That's the domain of that's contained inside of our curve. Our curve is traveling around, and you might not be able to see it, but there's an arrow here, and it's telling me what direction the curve is moving in, and it is moving in a counterclockwise direction. When a curve is moving in a counterclockwise direction, we say that it is positively oriented. So down here I've got a very big picture of going around an oval in a counterclockwise direction, and there's that positively oriented that's written on there. The negatively oriented is if you are traveling on the curve in a clockwise direction. So we have to remember that. Counterclockwise is positive orientation. Clockwise is negative orientation. Okay, and we'll see what the implications of that are later on in this section. So with Green's theorem, what we're told is if we have a curve and it's closed, simple closed curve, doesn't cross itself at all, and there's a region that is bound inside of that curve C, and if the components P and Q of our vector field have continuous first partial derivatives, then we get this really nice equality here. So first, the first two things right here are just stating what a line integral is. So the line integral over C of f dot dr is simply the line integral over C of p dx plus q dy. We're going with 2 dimensions right now. And what Green's theorem says is that instead of calculating the line integral over C, we can calculate a double integral over the region D of del q del x minus del p del y dA. So that is going to be like a volume, right? I'm not saying that it is a volume, I'm saying it's going to be like a volume because it's a double integral. That gives us area, the integrand gives us volume. And so we're finding this equivalency between a line integral and a particular volume integral. So equivalency between line integral and a special volume. Integral. Okay, so one of the things that you may see as well as you're reading your book and doing your homework is that when we do have a line integral over a curve C that is closed, you might see this notation where there's like a little circle that is halfway up on the integral symbol itself, and that is just to indicate that it is a line integral over a closed curve. Okay, so we'll just put that in here. Line integral over closed curve. Okay, now what it turns out, I don't know if you recall or not, but if we have a double integral and the integrand is 1, then that's also the same as just calculating the area of the region D. And so that's what I'm having you recall right here, is recall that the area of D is also calculated with a double integral over D of 1 dA. And so we could actually work this backwards and say that if we have an area problem, a double integral of 1 dA over some region D, and there's a curve that closes up that region D, then we can kind of work backwards and say, well, I could instead calculate a line integral over the curve that encloses the region D. Now, what we would have to do then is we would have to find a special P and Q value such that del Q del X minus del P del Y is actually equal to 1, so that then we could work backwards and, let's see, I want an arrow in there. We could work backwards and come, like, so we've come up with a P and a Q that del Q del X minus del P del Y gives us 1, then we could just take care of it using a line integral. Why would we do that? Because sometimes it's simpler. And that's honestly the only reason you ever use any of these theorems, is if they make life simpler. Now, if you don't remember them, then obviously that's not going to work. But they are there to make things simpler and sometimes even doable. So sometimes the line integral is treacherous. And so using Green's theorem to instead calculate a double integral of that difference of the first partials is an easier job. Or sometimes calculating the area of a region is treacherous. And so it'd be easier to just calculate a line integral over that. So I've got a few cases of different P and Q values. These are not the only P and Q values that would work. But for example, in case 1, so when I say P and Q, remember we're referring to the vector field F that has components P and Q. Okay, so we're like picking those. So if P was 0 and Q was X, then del Q del X would equal 1, and del P del Y would equal 0. And so that difference would be 1 minus 0, which is 1. So those would work as components of our vector field. In case 2, I have P is equal to minus 1 and Q is equal to 0. And so if we calculate del Q del X, we get 0. If we calculate del P del Y, we get a minus 1. So we have 0 minus a negative 1, which is 1. Those would work as well as components for our vector field. And similarly in case 3, if P is negative 1/2 Y and Q is 1/2 X, and we calculate the first partials, we will get 1/2 minus a negative 1/2 is equal to 1. And so we could choose any one of those situations, and if we forget those, we can make one up, okay? The only criteria is that the P and the Q that you choose should be such that if you were to calculate del Q del X minus del P del Y, you would want it to equal 1, okay? That's it. So in each of these cases that I gave, then we can come up with expressions for a line integral that will calculate the area of any region D that's bounded by a curve C. And so these are written out right here. Okay, now the curve C is going to be unique to whatever the region D is, but the integrand itself is just merely satisfying the criteria that I just talked about. So it's kind of weird, right? We're going to try to evaluate area, and instead of using a double integral over 1, we're going to go to a line integral to do so. Okay, all right, let's get to some examples. So in this particular one, we're going to use Green's theorem to evaluate the following line integrals. And in this one, we have that C is the boundary of a unit square, where X goes from 0 to 1 and Y goes from 0 to 1. So before I go any further, I'm going to draw that. All right, so I've got my axis, my XY axis. X is taking on values from 0 to 1. Y is taking on values from 0 to 1. And they have to do that in such a way that we've got a box formed. Okay. Now, this says that C is oriented counterclockwise. That means that we've got arrows that are moving in the counterclockwise direction. That also means positive orientation. And F is a vector field. F of xy equals e to the y plus x and x squared minus y. And we're supposed to find the line integral over C of f dot dr. Now, If we were in 16.2, then the way we would do this is the line integral over c of f dot dr would equal, well, first I would have to name my curve C1, C2, C3, and C4, and then I would have to calculate line integrals over C1 of f dot dr plus the line integral over C2 of f dot dr plus the line integral over C3 of f dot dr plus the line integral over C4 of f dot dr. Now, I don't know about you, but I don't want to do that. This is terrible, okay? So I want to use the fact that I have a closed region. So I'm going to use Green's theorem. Not to mention, I was told to use Green's theorem in the directions, but the reason is because we have the closed curve. All right, so remember Green's theorem, line integral over c of f dot dr, which we know to be the line integral over c of p dx plus q dy, is now going to be equal to the double integral over d of del q del x minus del p del y dA. Okay, so that means that the parts that we need to find are, for the integrand, we need those first partials. And for the differential, we need to just get bounds for dx and dy. Okay, so first things first, let's get our integrand. We have that p is equal to e to the y plus x. So del p del y is equal to e to the y. We have q is equal to x squared minus y, and del q del x is equal to 2x. Okay, so we're going to pop those in. I'm looking at my region. It is a rectangular region. It's actually square, but it's, a subset of a rectangle. And so my bounds are constant. For x and y, my bounds go from 0 to 1, 0 to 1. Okay, so del q del x minus del p del y is just equal to 2x minus e to the y. So I have my integrand. I know my bounds. I'm going to go ahead and pop them in. I have the integral from 0 to 1, integral from 0 to 1 of 2x minus e to the y, and I'm just going to go in the order of dy dx. Okay, now when I integrate this, I'm integrating first with respect to y. So I'm just handling that inner integral in the next step. And the integral with respect to y is going to be 2xy minus e to the y, and we will evaluate this from 0 to 1. Okay, I'm plugging in 1 for y and 0 for y, so this will be the integral from 0 to 1 of 2x minus e minus, in parentheses, 0 minus e to the 0, and then the dx. So I have a 2x, I have a minus e, and I'm going to get a plus 1 out of that double negative of e to the 0. So this will be the integral from 0 to 1 of 2x minus e plus 1 dx. All right, when I integrate this with respect to x, I get x squared minus ex plus x, going from 0 to 1. This is going to give me 1 minus e plus 1 minus, in parentheses, a whole big fat 0 comes from there. And my final answer is 2 minus e. Now, this calculation was a double integral, which is more than a single integral, but it wasn't 4 line integrals. I didn't have to parameterize 4 curves and then calculate 4 line integrals. I only had to calculate first partials, figure out my bounds, and then just go ahead and integrate. Okay? So hopefully that's some motivation for why we would use Green's theorem. All right. Now let's see. What do we have here? We have got C. This is supposed to be a positively oriented curve. I've got a mark in my notes saying that it's actually not positively oriented. So let's see what ends up happening there. I'm going to draw everything, and I'm also going to cross out this positively oriented curve. So let C be the curve consisting of line segments from, let's get an axis drawn. 0, 0 is the first point. 2, 3 is the second point. 2, 0 is the third point. So we're going 0, 0 to 2, 3, down to 2, 0, and then back over to 0, 0. This is negatively oriented. And so that because it has a clockwise rotation. Okay, so in this example, I'm going to tell you, here's how we handle having a negative orientation. Okay, what this means is that the line integral over the closed curve C of f dot dr is going to equal the negative of the double integral over d of del q del x minus del p del y dA. Okay, that's all we do. If it's going in the wrong direction, stick a negative in front of it. Okay. All right, so we've got our picture drawn. We know we need a negative sign, and now we need to figure out what P and Q are. So we know that f of x, y is equal to y squared, x squared, and the first component is P, the second component is Q. So if P equals y squared, I'm getting my integrand here. P equals y squared, then del P del y is equal to 2y. If Q is equal to x squared, then del Q del x is equal to 2x. All right, so then del Q del x minus del P del y is just equal to 2x minus 2y. All right, and then we've got to figure out our bounds as well. It looks like the line that connects 0, 0 to 2, 3, it looks like that has a y-intercept of 0 and a slope of 3/2. So this is y equals 3/2 x. And then, yeah, everything else is constant in there. So we can get our bounds. We have y is going from 0 up to 3/2 x, while x is going from 0 over to 2. Okay, so those are going to be our bounds. Let's plug everything in. We have the negative double integral, and the outer bound is going to be 0 to 2. The inner bound is 0 to 3/2 x. The integrand in parentheses is 2x minus 2y, and then we have dy dx. Right away, I am going to distribute that negative sign so that I don't lose it. Okay, so this becomes the integral from 0 to 2, the integral from 0 to 3/2 x of 2y minus 2x dy dx. Now that that's taken care of, I can, not worry about it. It's done, okay? All right, so we're going to integrate with respect to y first. The outer integral stays there, 0 to 2. And when we integrate 2y with respect to y, we get y squared. When we integrate 2x with respect to y, we get minus 2xy. We are evaluating from 0 to 3/2 x. And then we've got a dx on there at the end. All right, so plugging in 3/2 x for y will give us something. When we plug in 0, we will get no contribution. So this is going to leave us with the integral from 0 to 2 of, I'm going to write this, 3/2 x all squared minus 2x times 3/2 x minus 0 dx. Just showing myself everything there. All right, rewriting this so I can actually integrate it, we've got the integral from 0 to 2 of 9/4 x squared. And then we have a minus 3x squared dx. I could rewrite this so that I've got, I could rewrite it or not. They both have an x squared term, so I could combine them and then integrate, or I could just integrate them separately. Turns out it's easy enough to just integrate them separately. So I'm going to go ahead and do that. The antiderivative of x squared is 1/3 x cubed, which means I'll now have 9/12 x cubed minus x cubed from 0 to 2. All right, and plugging in my 2, that is going to give me 2 cubed is 8. So I get 72 over 12 minus 8. And that is going to leave me with a grand total of -2. I did do the calculations beforehand. So it will be a negative answer. Nothing wrong with a negative answer. It's weird, but it is possible, right? If we think of a line integral as being the amount of work done, it is possible to have negative work done. Remember, think like walking into the wind and the wind is pushing you. It's impeding your work ability. Okay. All right. The next example is for us to see how can we find the area of a region that is enclosed by a parametrized curve. And so this is going to be using Green's theorem in the opposite way. Okay. Integrating over this curve seems a little, well, I mean, I have my parametrized curve, but it seems a little rough, especially if I want to just find the area of the region. So, and I'm sorry, I meant to say the opposite of that. Finding the area of that region seems really hard using a double integral. I would like to use a line integral. Okay, so this area would be very complicated to calculate the area. Using Green's theorem, we can use a line integral to calculate the area instead of a double integral. And to be quite honest, I'm looking at this and I don't know a function that would give me that strange loop right there. I have a parametric curve, but I'm not sure what my function would be, right? So if we wanted to use that double integral and go back to like chapter 15 in order to calculate the area of a region, I don't know, okay? So that's the big problem here. Our region, our area, is inside of that curve, okay? So let's see. We need, so Green's theorem, my R's, E's, and N's are all looking the same. So Green's theorem says the area is equal to the double integral over d of 1 dA, which is equal to the line integral over the closed curve C of p dx plus q dy, where del q del x minus del p del y is equal to 1. So we need to choose p and q so that del q del x minus del p del y is equal to 1. Now I'm going to go different from the cases that we had up above just to show you that you really can pick whatever you want. So I'm going to go ahead and let p equal 2y and q equal 3x. Then del p del y is equal to 2, and del q del x is equal to 3. And the difference between the del q del x and the del p del y is equal to 3 minus 2, which is 1. So I have what I need using those two functions, okay? So that means now we can go back to our area formula. Area, which normally we would do the double integral over d of 1 dA, is equal to the line integral over c of p dx, and p is 2y dx, plus q dy, q is 3x, and then a dy. Okay, so that's the line integral that we're going to use to calculate the area. Now, we know that the curve C is defined by r of t, which was given up above, has components t minus t squared and t minus t cubed, and t goes from 0 to 1. Okay, remember that the components in r of t are the x of t and y of t values that we need to plug into our line integral. But we also need to know what r prime of t is, because we need to get dx and dy, right? So we know that r prime of t dt is going to equal, well, let's go ahead and take derivatives, 1 minus 2t, and then 1 minus 3t squared, and then dt. And so these are the x prime of t values and y prime of t values, and these will equal our dx and dy that we need to replace. Okay, so with all that said, we're going to go and plug everything in. We know our bounds are 0 to 1. 2y, okay, well, everywhere there's a y, I need to use the y component of r of t, which is t minus t cubed. dx is going to be that first component of r prime, so it's 1 minus 2t dt, plus 3 times x, and x is coming from the first component of r of t, and it is t minus t squared, times dy, which is coming from r prime of t, that'll be 1 minus 3t squared dt. Okay, now this is a bit of an algebraic nightmare in the fact that we have to FOIL out two things, but it's still easier than trying to calculate the area of a region when we don't have a function for that area. So let's go ahead and FOIL out. This will give us the integral from 0 to 1 of, let's see, we get 2 times, and then when I FOIL this out, I've got t minus 2t squared minus t cubed plus 2t to the 4th plus 3 times t minus 3t cubed minus t squared plus 3t to the 4th, and then put some big brackets around there, and we've got our dt on the outside. Okay, 2 more steps. Integral from 0 to 1 of, it looks like we've got 4t to the 4th minus 2t cubed minus 4t squared plus 2t. And then we have plus 9t to the 4th minus 9t cubed minus 3t squared plus 3t dt. Now I will combine like terms. The integral from 0 to 1. I have t to the 4th terms that add to 13t to the 4th. I have t cubed terms that add to negative 11t cubed. I have t squared terms that add to negative 7t squared. And then I have t terms that add to 5t. And then I think those numbers are all good, dt. All right, now we can go ahead and integrate. This is going to be 13 fifths t to the 5th minus 11 fourths t to the 4th minus 7 thirds t cubed plus 5 halves t squared, evaluated from 0 to 1. There is no contribution from 0. All the contribution is from 1. looks like we are adding up 13 fifths minus 11 fourths minus 7 thirds plus 5 halves. Make sure you have a good calculator that can add fractions and give you a fraction. This adds up to, I should put my minus 0 in, this adds up to 1 over 60 for a final answer. And this is equal to the area of the region. Still a long process. I'm not going to say that the process is short, but it's possible. Whereas before it really wasn't possible because we had no way to give that region any sort of function. Okay. All right. Next one, we are to evaluate the line integral over C of x to the fourth dx plus xy dy, where C is a triangular curve consisting of the line segments 0, 0 to 1, 0, then from 1, 0 to 0, 1, and from 0, 1 to 0, 0. First things first, we got to draw that region and figure out if we've got positive orientation or negative orientation. So let's go ahead and draw ourselves a nice xy axis. Starting at 0, 0, we're told to go to 1, 0. And then we're told to go to 0, 1. And then back down to 0, 0. So this is counterclockwise rotation, which is positive orientation. And what that means is that we should be able to take this line integral over C of x to the fourth dx plus xy dy, and instead plug it into a double integral over d of del q del x minus del p del y dA. That just means we have to figure out all the parts, right? We need our bounds for our integrals, and then we need our integrand. So I'm going to go to our picture first and come up with the equation of that line. It looks like it has a slope of -1. So we have y equals a negative x, and then the y-intercept is 1. So this is negative x plus 1. Okay? And from what I can see here, it looks like y goes from 0 up to, I'm going to rewrite this as 1 minus x. And at the same time, x is going from 0 to 1. So we have our bounds. We need to calculate del q del x minus del p del y. So for our integrand, from the given integral, we have that p is equal to x to the fourth, because that is the function that is with dx. That's how I know it's p. Del p del y is equal to 0. Q is equal to xy, and del q del x is equal to y. So then the difference, del q del x minus del p del y, is just equal to y. So that's our integrand. Let's go ahead and plug everything in. This is going to be, the outer integral goes from 0 to 1. Inner integral goes from 0 to 1 minus x. The integrand is y, and we're going dy dx. That's a nice simple double integral. All right, so when we integrate with respect to y, we still have the 0 to 1 on the outside, and we have a 1/2 y squared for an antiderivative. We'll evaluate that from 0 to 1 minus x, and then a dx. Evaluating at 1 minus x, I have the integral from 0 to 1 of 1/2 times 1 minus x all squared, and then a minus 0. So I'm going to do this as a u sub, just because I know that a lot of people will FOIL this out, and that's okay if that's the only thing you have to FOIL out. But if you have multiple things to FOIL out, it's good to use u subs. You can avoid algebraic errors in FOILing, as well as simplify your whole process. So I'm going to do a u sub. My u sub is to let u equal the 1 minus x. Then du is equal to minus dx. So I'm really going to replace dx with a negative du. So then if I have the 1/2 in there, this will be negative 1/2 integral of u squared du, which is just negative 1/6 u cubed. All right, let's go ahead and plug that in. So this gives me a negative 1/6 times 1 minus x all cubed, evaluated from 0 to 1. That'll be, I'll pull out the negative 1/6 and evaluate at 1. I get 1 minus 1 all cubed minus 1 minus 0 all cubed. So the first term goes to 0. The second term is a minus 1. So this is minus 1/6 times minus 1 for a grand total of just 1/6. All right, so that is the value of the line integral using Green's theorem. It was much easier than using 3 line integrals, because if you notice, that triangle would need a C1, a C2, and a C3. So we'd have to parameterize all 3 of the curves and then calculate 3 line integrals over each curve. Okay, much nicer to just do a double integral. All right, last problem. I think this is the last one. Second to last problem. Okay, we're going to evaluate a line integral over the closed curve of 3y e to the sine of x dx plus 7x plus the square root of y to the 4th plus 1 dy, where c is the circle x squared plus y squared equals 9. I'm already looking at those values in there, and they look horrible. This is going to be one of those situations where I can't actually evaluate the line integral. Okay? I am going to need to use Green's theorem for sure. So I have that C is a circle, and they're telling me it's the full circle, which means Green's theorem. So notice in the instructions, they never said use Green's theorem. It is up to you to know when you could use it or when you can't use it. Okay? So if I draw this, I have a circle of radius 3. All right, we're going to assume positive orientation and get that 3 in there. Okay, so our domain D is defined by the region x squared plus y squared is less than or equal to 9. So we have a circular region, right? We're going to be looking at integrating over all of the inside here, okay? So we have to remember, how would we handle the situation where we are integrating over a full circle? Well, we would go to polar. That's the easiest way to do this. I definitely do not want to solve for y squared in terms of x and have square roots in this horrible problem to begin with. So I am going to go ahead and say, in polar, we would have the r goes from 0 to 3, and theta goes between 0 and 2 pi. I'm just going to put that aside for a moment, and I'm going to look at my parts that I need. I know that I am dealing with a closed line integral, and then I'm going to switch to Green's theorem. So I'm going to identify my p and my q. P is 3y minus e to the sine of x. Del p del y is equal to 3. That's much nicer than p. Del q del x, sorry, let me start with q. Q is equal to 7x plus the square root of y to the 4th plus 1. Del q del x is equal to 7. Also much, much nicer. So what we have here is a line integral over a closed curve C of f dot dr is equal to, the way we have it written actually is not f dot dr. Let me write it in the alternate notation. It's p dx plus q dy. Instead of dealing with that, we're going to look at the double integral over d of del q del x minus del p del y dA. All right, and we're going to automatically switch right over to polar coordinates. And so this will be the integrals. I'm going to get my 7 minus 3 in there. And since dA is going to go to polar, we have r dr d theta, right? So r dr d theta, I'm putting r in the inner integral, so it's 0 to 3. Outer integral is for theta, 0 to 2 pi. Looks like we're ready to go. 7 minus 3 is 4, right? So we have 4r in there. If we integrate 4r, we get 2r squared. We evaluate from 0 to 3. And then after we evaluate that, we'll integrate with respect to theta. Plugging in 3, I get 18. So the integral from 0 to 2 pi of 18 d theta. And then that gives me 18 theta from 0 to 2 pi, which is finally going to give me, 36 pi. So what happened here is I started with a problem that had horrible P's and Q's in it, like just horrible. If you think about how we would parametrize a circle, especially this one, r of t would have been 3 cosine of t and 3 sine of t. Now imagine those replacing all the x's and the y's in the pdx and the qdy. So that e to the sine of x would now be e to the sine of 3 cosine of t. I don't know how to integrate that. Like that's crazy stuff. The square root of y to the 4th plus 1 would now be the square root of 81 sine to the 4th plus 1. I don't know how to handle that either. So there's a huge advantage. If you've got a horrible vector field, Green's and a closed curve, Green's theorem will save you from that. Okay. The last thing that comes up here is that we are asked if F is a conservative vector field and C is a closed curve with F continuous on C, what happens when we apply Green's theorem? Okay, well, let's start from what we're first given. F is conservative. And we have to ask ourselves, well, what does that mean? Well, it means that F is equal to a gradient vector field that has components P and Q, or as I was stressing in the previous video, components F sub x and F sub y. Well, if we know that F is conservative, we also know that this means that del P del y is equal to del Q del x. Okay? That's the first implication. C is a closed curve. That implies to use Green's theorem. Okay, so then we would have a line integral over C, closed curve, of del f dot dr, which would equal the double integral over d of del q del x minus del p del y dA. But if del p del y and del q del x are equal, this means we're looking at the double integral over d dA of 0, which gives us 0. So integrating a conservative vector field over a closed curve will always result in 0. Okay, and that's it. We're done. If you have any questions at all, please reach out.